So hello dear students. So in this consecutive lecture on uniformly accelerated motion, I'm going to discuss different graphical techniques that are employed to understand different type of motions like uniform velocity motion or uniformly accelerated motion. And we will understand what information we can derive from these graphs. And also we will discuss certain different types of uniformly accelerated motions, like for example a free fall, which is that is under the gravitational pull. If an object is falling freely, or if you throw an object upwards and it is moving in a straight line upwards, in that case again it's a uniformly accelerating motion because a uniform gravitational force is acting upon that object. So let us first of all understand the different types of graphs that we can have in this kind of a scenario where we are talking about a uniformly accelerated motion. So let us start with graphical analysis. Okay, so first of all we'll understand the position type or the let us say the displacement time graph. Okay, so in this, on the y-axis you plot the position or the displacement. On the y-axis you have the displacement x, and on the x-axis you plot time. Okay, so in that case, let us say if you have a straight line graph like this to start with, then as you already know, as we have discussed earlier also, this represents a uniform velocity. That is, the velocity is not changing with time because the slope of the graph is not changing with time. So that means, and you know the slope of the graph of a position time graph, that is dx by dt, which is the slope of the graph, is related to velocity. It is actually equal to the velocity. And this slope, as you can see, is not changing with time. So this slope is not changing anywhere. So that means the velocity is constant. Similarly, if you have a graph like this, that is a position time graph, which is a parabola. So if it is a parabola, then in that case you can say that the graph represents a uniformly accelerated motion. Okay? And why is it so that a parabola represents a uniformly accelerated motion? So you can understand it like this, that you know that you have the one equation of motion that we have earlier understood was x minus x naught is equal to ut plus half at square. So this was the equation that we had discussed earlier in the previous lecture. And if you see from this equation, the displacement s is related to time in a quadratic fashion. So it's a S is ut plus half at square. So basically, if the acceleration is time independent, then this equation is nothing but just a, what you can say, it is a quadratic equation. And when it is a quadratic equation, in that case, what actually would happen is that the graph between the displacement and time is going to be parabolic, because a quadratic equation always has a parabolic graph. Okay, so I hope you understand what is the basic, what you can say, reason why this particular graph of uniformly accelerated motion is parabolic. Okay. Now let us now talk about a velocity time graph. Okay. So in that case, the y-axis would represent the velocity and the x-axis would represent again the time. Okay. And the slope of the graph. Let us say if you have some graph with arbitrary curve, and then the slope of the graph at each point. Let's say at this point, or at this point, or at this point. So this slope would represent what? You know, every this thing that the slope is represented by the derivative of the function with respect to the variable. So it is basically, in this case, is going to be just dv by dt. So this is the slope at each point on the graph. So as you know from the definition of acceleration, this quantity is represented as acceleration only. So dv by dt is actually acceleration. So the slope of the velocity time graph is going to give you the acceleration. Whereas if you talk about the area under the graph, let us say from here to here, we're talking about this area. Under the graph from point A to point B. So this area is represented by, let us say, area is always represented by the integral. Okay, so this is the area, and this, as you know, will, if you know that velocity is dv px by dt, so this integral will then give you which would be equal to xa minus xb. So simply stated, the area under the integral is going to give you the displacement. Okay, so you can see that the velocity time graph contains the information about the acceleration as well as about the displacement. So it is an intermediary graph. The position time graph is one graph and acceleration time graph is another graph. But the velocity time graph is going to give you information about both these, both the position and the time graph as well as the acceleration and the time graph. The slope of the velocity time curve is going to give you the acceleration, and the area under the curve of the velocity time graph is going to give you the displacement. Then let us talk about acceleration time graph. Okay, and in this acceleration time graph, again on the y-axis you have now acceleration, because it's the acceleration time graph, and on the x-axis you have time, and it would be very evident to you for a constant acceleration or a uniform accelerated motion, the graph would be a straight line or a horizontal line, because the acceleration is not changing. And any other graph or any other form of the graph whether this one or anything, any other shape of the graph is going to represent a changing acceleration. That is an acceleration that is changing with time. And though then in that case there will be some rate of change of acceleration which is known as the jerk. So the jerk is known as the rate of change of acceleration. So in this particular graph you have a non-zero jerk. Whereas here in this particular graph you have a uniformly accelerated motion. Okay, and what is the area under the graph? Let us say here to here, from point A to point B. If you have this area is going to represent the change in the velocity. Now, okay, so the area is going to be equal to VB minus VA. So whatever was the velocity at point B minus the velocity at point A on the time axis. So that change in velocity is going to be represented by the area. So I think these kind of things are pretty much clear to you. So let us now take a case of motion under gravity. Case that is motion under gravity. So in that case, what is happening is an object is subjected to a uniform force of gravity, that is, it is situated somewhere above the ground and it is being pulled by the earth towards its center with a uniformly acting force. So let us say we are discussing motion under gravity, and let us say there is an object which is situated somewhere above the ground, and this is the ground you have. And so this object is somewhere above the ground and it is being pulled by the earth with some uniform force which is dependent upon the mass of the object and a quantity called g, which is called the acceleration due to gravity. So what is happening? This g that you talk of is called the acceleration due to gravity, okay? And what you can understand is it's like this. That is, if an object is there somewhere above the ground and you allow it to fall freely, that is, you drop that object and it is falling down So it is falling and it is having an acceleration. So it is actually an accelerated motion. It's not a uniformly velocity or uniform velocity motion. The velocity of the particle or the object is changing as it is falling towards the ground. It is actually increasing. The magnitude of the velocity is increasing with time as it is falling towards the ground. And it is because of the fact that a force is acting on that object, which is the gravitational force, and it is proportional to the mass of that object, and also it is proportional, or rather it is related to the acceleration that it produces. So it is nothing but the force is equal to mg in this case. It is a slightly different form of the well-known equation of Newton, which is force is equal to ma. So mass in times acceleration is force, which you will learn later on. But in this particular case, the acceleration turns out to be g, which is the acceleration due to gravity. And its value is 9.8 meters per second square. So always remember the value of g is 9.8 meters per second square, and it is always directed towards the ground, towards down. So if your axis is like this, that you take up as positive and down as negative, then the direction of the g is always down towards the earth, towards the center of the earth. So g would always be negative. But you have to follow this sign convention that up is always positive and down is always negative. So according to this sign convention, the value of g is going to be negative. Okay, so it will be negative. But if you take the reverse sign convention, which in this case, if you take up as negative and down as positive, that in that case, g would be positive. Or the value of g would not be minus 9.8 meters per second, but would be plus 9.8 meters per second. Okay? So let us illustrate this with the help of an example. So let us say we have made the origin as the ground. So this origin is the ground, and the initial position of this object here is s, which is 20 meters. So you can say this is x or s, okay, and it is 20 meters, and when it comes to the ground, once it falls and reaches the ground, the value that it has now of the position is 0. So you can say that x final minus x initial is what? That is the total displacement, and it is equal to 20 minus 0, which is equal to 20 meters. And at the time when it was dropped, at that time its velocity was 0. So when it was dropped, then at that point of time its velocity was 0. So the initial velocity u is 0. So you have, now what is asked is how much time will it take to reach the ground? So this is the question, and we will use two different sign conventions. One of them is the sign convention in which you have upward as positive and downward as negative, and the other sign convention where you have upward as negative and downward as positive. So let us first use the first one where upward is positive. So in that case the displacement is 20 meters per second, and u is 0, and then we use this formula s is equal to ut plus half at square. Okay, so s is 20, then u is 0 plus half. Now a is actually g, because in this case it is a motion under gravity. So the acceleration produced by the in the object would be the acceleration that is produced by the force of gravity. So then in that case acceleration would be equal to g. And we have already said that in the this particular sign convention that we are talking about, the value of g is negative. So then you have minus 9.8, then you have t square. Okay, all right. And then of course we have made a mistake here. It is not 20 but minus 20. As you can see here, the final position xf is this, and the initial position xi is this. Why? Because it is the position at the start of the motion, and this is the position at the end of the motion. Okay, so it is going to be 0 minus 20, which is going to be minus 20. So here you have a minus here. Okay, so then you can say that t square is going to be equal to 2 into 20 over 9.8, which is then under root of this will give you t, and it turns out to be equal to 2.02 second. Okay, so this is what we have done using the sign convention where up is positive and down is negative. Now we will repeat the same problem with the sign convention in which the down is positive and the up is negative. And in that case, you know, the sign of the acceleration due to gravity is positive, because down is negative, down is positive, so acceleration due to gravity is also in the downward direction. So since down is positive, so the acceleration due to gravity is also positive. So let us do it by the other method in which, okay, so in this sign convention, your value of g is going to be equal to plus 9.8 meters per second square, and then the x initial is 20, x finally, x initial now is going to be minus 20. Okay, so why it would be minus 20? Because up is negative and down is positive. So you are going from down to up towards positive to negative. So in that case, your x initial is minus 20 meters. So then what is the displacement? S is equal to xf minus xi. So xf is 0, and then minus of minus 20, which is going to be equal to 20. Okay? And then we use the equation S is equal to ut plus half at square. So S is 20 and u is 0 as always, plus half. Then you have g is equal to plus 9.8 and then t square. So again, when you calculate, your t becomes equal to 2 into 20 over 9.8 under root, which again is equal to 2.02 second. Okay. So you see in both the cases, we have the same result. The time is 2.02 meters per second. Oh, sorry, 2.202 second. So let us now do another problem. Let us say you have a graph here. It's a velocity time graph. So it is of an object that is moving in straight line, but it can be accelerated motion, but in our case it is going to be uniformly accelerated motion. So the time it has taken for the whole motion is from 0 to 2 seconds. Okay? And then what is happening is at 1.5 second, till that point, it is actually moving at a uniform velocity, which is negative in this case. So it has got some uniform velocity which is negative till this point. Well, let us say its velocity was 1 meters per second. And then after that, it started moving with a uniform acceleration. So let us say it's moved till this point with a uniform acceleration. So a uniform acceleration would obviously represent a straight line on a velocity time graph. Now what he is asking is, what in this kind of a situation, what you can, from the area, what will you get? You will get the total displacement. Okay, from the area you are going to get the total displacement. So he's asking you what is the total displacement. So in this case, we will calculate the areas. So let us say this point is A, this point is B, C, D and E. So first of all, we'll find the area A, B, C, D. Okay, which will be the area of this rectangle, and it is going to be the height times the breadth, and the height is -1 and the breadth is from 1.5 to 0, that is 1.5 minus 0. So it is going to be minus 1.5. This much would be the area, and in the, what would be the units? This is velocity and this is time. So velocity times time is going to give you displacement. So the unit is going to be meters. And the negative shows that the displacement is negative, because displacement turns out to be a vector quantity and it has got a sign in one dimension. So it is negative because the sign is negative, and also you can see from the area which is below the x-axis. So the area below the x-axis is always taken as negative area. So in that case, you can say that this would be the displacement from point A to B. And what about from point B to C? So that would be the area of triangle BCB. and it would be nothing but half times the base, and the base is again minus half times the height. First of all, so height is -1, and what about the base? Base is 2 minus 1.5. Okay, so this is the base, BC is the base, so it is 2 minus 1.5, and so it will turn out to be equal to minus times 2 minus 1.5 is 0.5 by 2, which would be equal to minus 0.25, again in the units of meters. Okay, so now in this case again you are seeing that the total displacement from let us say from 0 seconds to 2 seconds in this particular motion, which is represented by this graph, is going to be the area under this whole curve from A to C, and then it would be equal to minus 1.5 plus minus 0.25, which would be equal to minus 1.75 meters. So this is the actual displacement, and it is actually a negative displacement. So basically it is moving, you can say, along the negative x direction. So the x direction is negative rather than being positive. So it is moving along the negative direction. Okay. So you can do a lot of other problems, like for example, a car is moving along a straight highway. So you have a car which is moving along the highway with a speed of 126 km per hour. So this is the speed. And it is brought to a stop. Suddenly, at this point, let us say at this point x naught, it is having a speed of 126 km per hour. So suddenly, within a distance of 200 meters, it is brought to a halt. Okay, so now it stops. So now its speed is 0. So what is the retardation? He's asking. And how long does it take to stop this car? So within the distance span of 2200 meters, a car which was initially moving with a speed of 126 km comes to a stop. And he's asking what was the retardation or the deacceleration of the car, assuming that the deacceleration was uniform, and how long does it take to stop? These are the two questions. So first of all, you know that the initial velocity u is 126 km per hour. And since the displacement is given in meters, so you have to change the units. This is in kilometers per hour and the displacement is in meters. So the displacement is in SI units, and this one is not in the SI units. The U is not in the SI unit. So you change it. So you do it by this. So 126 into 1000 meters for the kilometer, and for the R you have 3600 seconds. Okay. So then you have, when you do this, you have 35 meters per second. Okay. Now, once you have 35 meters per second here, as u, then the displacement is, or rather the s, Okay. Then what is he asking? The first question that he has asked is what is the deceleration. So you will use this formula. V is equal to U plus 2AS. This is one equation of motion, or sorry, V square. Okay. So you know U as it is given here, and you also know V. So after covering 200 meters, V becomes 0. The final velocity becomes 0. So V is also known, U is known, then you have to calculate S. Then what will you do? You will use this equation. 0 is equal to 35 square plus 2A, and the S is 200 meters. So then, of course, A turns out to be equal to minus 35 square, okay, divided by 2 into 200. So when you calculate it, it turns out to be equal to minus 3.0625 meters per second square. So you can see the sign here is negative. So the retardation is negative because it is the deceleration, and deceleration means that the velocity is reducing with time. As the time is changing, the velocity is reducing. So that is the deceleration, and it is always negative. Whereas when the velocity is increasing with time, then you have acceleration and not deceleration, and that acceleration is going to be positive. So deceleration is negative and it is the value. And then the next part is, that is the first part. Okay, then the second part is about the time taken. So you will use this formula then. S is equal to ut plus half at square. So S is given to be 200 meters, the total displacement. U was, of course, 35. Okay, so 35 into T plus half. Then you have A, which is minus 3.0625 times T square. Okay, and then from here you can calculate the value of T. So this is a quadratic equation, and when you solve this quadratic equation, the T would have a value. One of the roots of the quadratic equation would be 11.43 seconds. So this is a quadratic equation, and using this quadratic equation you can actually solve it. Okay, and then you can solve it by another method, using the another equation of motion, which is V is equal to U plus AT. Okay, and then in that case V is 0 and U is 35 plus, then A is minus 3.60625 times T, and then T would be again 35 by 3.0625, and this would again give you 11.43 seconds. So you see, you can compare the answers you get from the two different equations, and then you will see that both the equations are going to give you the same answer. So you can understand all these equations of motions are related to each other, and if you have extra information, then you can use actually two equations, two different equations, if you have an extra variable that is also known to you, and then you will find, then if the your motion is consistent and everything is perfect, then you will get the same answer in both the cases. Okay, so that is how we are going to use the equations of motions, and how we can understand what an acceleration is, what is deceleration is, and what is the sign convention that is used when you're talking about acceleration due to gravity. These are the few important things that you must remember while you are tackling uniform acceleration and the problems that are connected with this particular chapter. Okay, so